Today I want to talk about the one type of electrochemical cell that we haven't talked about, and that is what we call electrolytic cells. So everything that we've talked about so far has been dealing with what we call a voltaic cell, right, which deals with spontaneous reactions. So the other kind of electrochemical cell is what we call an electrolytic cell. And this is one where we can force, in other words, drive a non-spontaneous reaction to occur. So if we think back and just sort of look at electrochemical cells, so whether you have a voltaic cell or one of these electrolytic cells, we will always have oxidation occurring at the anode, reduction at the cathode. Right? So that sort of nomenclature is going to stay the same. In the voltaic cells that we looked at, the key is we're looking at spontaneous reactions that generate electricity, right? Spontaneous redox reactions, where the anode is producing the electrons via oxidation, the cathode is drawing those electrons to it and undergoing reduction. And we use the negative and the positive sign for our anode and cathode. In electrolytic cells, right, we are going to be looking at non-spontaneous reactions that are driven by some external current. Right? So we have to supply the energy to the cell, right? Now, we typically do this by attaching some sort of DC current or battery to it. So if we look at an example of electrolysis. So electrolysis is the most common type of reaction that we're driving in these electrolytic cells. And essentially what electrolysis is using electrical current to drive a non-spontaneous reaction. So the reactions that we look at here can sort of generally be called electrolysis reactions because that's what we're doing. We call this, again, an electrolytic cell. Now, we're going to look at some specific uses of this. So one of them is to separate compounds into their elements. So in other words, to break down a compound into its elements. We're going to look at, just briefly, example of converting metal ionic compounds like oxides or chlorides, right, back into the basic metal. And electroplating, which is sort of an application of this idea of converting metal ions back into the metal. Now, we saw earlier in a fuel cell that we could take oxygen and hydrogen and produce water, right, in a fuel cell. Well, we can drive the opposite reaction or the reverse reaction in an electrolytic cell with the electrolysis of water. So by hooking up an electrolytic cell, and so in the way an electrolytic cell works is we have our cathode hooked up to the negative terminal of our battery, right? And so electrons are going to be flowing out of here, right? So remember, this is the anode of our battery. And so we're essentially forcing electrons into the cathode, okay, to cause the reduction. Okay. Now, this reduction, okay, we get an oxidation, right? And the oxidation occurs and the electrons flow back out of the anode back to the positive terminal of the battery or the cathode of the battery. Right? So just like when you hook up a battery to any sort of application, right? Hook up with your calculator, the electrons flow out of the negative terminal of your battery through whatever device and do whatever work you're asking them to do, and then flow back into the cathode of the battery. That's what's going on here. The work that's being done, right, is driving or running this electrolysis reaction. And so here we're breaking down the water at the cathode. We're taking the hydrogen of the positive 1 and we're forcing it back to hydrogen 0, right, to gain that electron to form hydrogen gas. And at the anode, we're taking that oxygen with a -2 oxidation state. It's giving up its electrons to go back to oxygen 0 or oxygen gas. And so we're forming our elements from our compound. Now, some people always comment on the size of the balloons. So this we can easily understand by understanding the stoichiometry, right? Because to make water, we have to produce 2 moles of hydrogen to 1 mole of oxygen. And so we get a 2-to-1 stoichiometry. So as water breaks down, we form 2 moles of hydrogen gas to every 1 mole of oxygen gas. Now, if we look at the basic setup of these cells, you'll notice some similarities, right? So if we have the voltaic cell, right? So this is in the spontaneous direction, right? We get a 1.1 voltage, right? We have our classic zinc copper voltaic cell. If we look at the electrolytic application of this, where we're hooking this up to some sort of voltage source, and again, we're forcing this to run in reverse. So out of the negative terminal, we drive the electrons back into the cathode. Notice this picture has been reversed, right? So now we have the zinc is functioning as our cathode, right? And so we're getting zinc ions to go back to zinc metal. And then at what is now the anode, the copper metal is being formed into copper ions, and the electrons are being given off and going back to the battery. Right? So in this way we can drive the zinc to zinc metal and the copper to copper ions. Or in other words, we can do the reverse reaction, right? We can do the non-spontaneous direction. So the zinc oxidation is the spontaneous direction. The copper oxidation would be the non-spontaneous direction. Now, notice in order to drive this, we have to supply a voltage that is at least equal, but typically greater than whatever the spontaneous voltage that we get out. So if this cell is 1.1 volts, then to drive it backwards, we would have to supply at least typically more than that 1.1 volts to drive it backwards. So if we just kind of sit back and look again at our electrolytic cells, so remember, electrons are being drawn away from the anode of the battery, or from the anode of our electrolytic cell, and this is going to be connected to the positive terminal of the battery, or in other words, the cathode of the battery, right? So for example, the graphite rod, right? If we were talking about an alkaline battery. And electrons are forced to the cathode of our electrolytic cell by hooking it up to the anode, or the negative terminal of the power source, where the electrons flow out. So the electrons flow from the battery to the cathode, where the reduction takes place, and the oxidation produces electrons which flow back to the positive terminal of the battery to complete the circuit. Okay. Again, this is the sort of reverse, where we have the spontaneous fuel cell reaction, or we can non-spontaneously drive what we call the electrolysis of water, right? The breakdown of water back to its elements. And that electrical energy comes from some sort of direct current. Most common, right, would be a battery of some sort. It could also be a power supply unit that you have, DC power supply unit, which these are often used if you run a lot of these things where you can adjust the current up and down, or battery is going to give you a sort of a constant current. Now, this is what I mentioned too, this quote overvoltage, where a lot of these reactions require you to deliver more voltage than what the cell would require in the spontaneous direction. So we saw that if it produced 1.1 volts in the voltaic version, we'd have to supply more than that to drive it backwards. And so this is the idea of, when you recharge your phone, of course, you have to plug it in, right? You have to supply some power to it, and this is in the form of electrical power, the DC power out of the wall, right, in order to drive that reaction backwards. And the charger, right, makes sure that you apply the right current, right, the right voltage, the right voltage to that battery so that you get enough voltage but not too much voltage so that you damage the battery. So if we look at some of the examples or some of the uses of this technology, right, we can do electrolysis of what we call pure compounds. So this is where we take some sort of pure, we're going to use the example of an ionic compound, right? And we convert it back to its elements. So we saw this with water, but now we'll look at it with metallic compounds. Now, the key is, right, we have to deal in the liquid phase here. We can't be just hooking this up to a big solid salt sample, right? We typically use inert electrodes like graphite, right? We don't use the metals. This is a lot of times for practical reasons and for simplicity, right? Because we often operate at high temperatures here. And, of course, the cations, right? And so this is going to be the metals, typically, are going to be reduced back to the metal form. And your anions, so these are going to be typically your nonmetals, they're going to be oxidized back to their elemental form. Back to the nonmetal element. So if we take an example here, and this is the electrolysis of molten salt or sodium chloride. So imagine we have a vat here of molten sodium chloride. So it's going to be very high temperature. Remember, sodium chloride melts around 800 or so degrees. So it's going to be very hot. You hook this up to your power supply, and at your cathode, right, we're going to have reduction of the metal. Right? So in this case, the sodium plus ions are going to be converted into sodium metal. And at your anode, you're going to have the oxidation where your chloride ions in this case are going to be converted back to the nonmetal element or chlorine gas. And the electrons are going to flow back to your voltage source. Now, this is how we get sodium metal, right? This is one of the major ways we get it, because remember, these alkali metals especially, right, are not found in nature in their pure form. They're only found as ionic compounds. And so the only way that we can get these pure metals is by some sort of chemical way. And the most common way to do that is via electrolysis. We get a lot of metals this way: sodium, magnesium, a lot of our aluminum. Something called the Hall process comes in this kind of idea, where we'll take aluminum oxides that are found in the earth Right? So most metals, in fact, are found as ions, right? They're found as compounds, whether these be oxides or halides or some sort of what we would generically call ore or compounds. And if we want the pure metal, we have to chemically convert them back to the pure metal. And electrolysis is one of the common ways that we do this. Now, what if we have a mixture of ions? So what if we didn't just have pure sodium chloride, but we had sodium and another metal in there as well? Well, basically, if we have more than one cation, the cation that is the easiest to reduce. So if we look back at our reduction potential table, the one that had would be the most easily to reduce on that table. So it has the most positive or least negative reduction potential, right? So the one that is at, in this case, the very top of the table. So the most positive reduction potential, meaning it's most likely to be reduced, that's the one that's going to be reduced first. And if that one will run out, well, then we could start to reduce the other ones. So you don't typically run into these problems where you're producing, multiple different metals. Typically, you'll have the one that's easiest to reduce first, and then the second one. And same thing at the anodes, right? The negative ion, the one that is the one that is the easiest to oxidize, will have the least negative, most positive oxidation potential. If you want to think of it as reduction potential, this would be the most negative reduction potential. So one's closest to, the bottom in your reduction potential table. Now, one of the things we can do in an electrochemical cell, an electrolysis cell, is that we can utilize what we know about how this reaction occurs, and we can predict pretty accurately how much metal that we're going to make. Now, while this might not be so important in, say, bulk electrolysis, right, where we're trying to just make bulk metal, it can be extremely important if we're trying to control the amount of metal that we make. And another application that we'll touch on here, which is electroplating, right, where we're trying to produce a specific amount of metal on a surface or something to that effect. So we can do what we call stoichiometry of electrolysis, where this is where we can predict how much metal is going to be formed or how long it's going to take to produce a specific amount of metal by understanding the electrons, the stoichiometry of the electrons. So we're going to essentially treat electrons in this application as an actual reactant in our process. Now, so what we need to figure out is the moles of electrons that flow through an electrolytic cell. And this is dependent on two factors: the amount of current that we put through it and how long we run that current through it. So a couple of things to remember. Remember earlier we said that 1 amp of current is equal to 1 coulomb per second. Okay? So 1 amp equals 1 coulomb per second. So if you run 2 amps, it's 2 coulombs per second, etc. And remember, Faraday's constant tells me the amount of coulombs, or how much charge, is in 1 mole of electrons. So the basic layout of a problem might be, okay, if I know that I run it for a certain amount of time, I can then run that for a certain number of seconds, so I can get my time into seconds. Then if I know the current that I use, I can see the total amount of charge that would have been put through. So if I'm running 5.5 amps, let's say, I put 535 coulombs per every second. So if I run it for 100 seconds, well, I'm going to put 100 times that through. So I can essentially calculate the total charge that I'm putting through by running a certain current at a certain time. Now that charge is going to be equivalent to a certain number of moles of electrons according to Faraday's constant. So I'm going to take that total charge, divide by Faraday's constant, or divide by the 96,025, and that'll tell me how many moles of electrons I'm running through this cell. And by understanding the stoichiometry of our electrochemical reaction, in other words, how many electrons I need to make a mole of metal. So is it a 2 electron? Am I going from, say, 0 to positive, or positive 2 to 0? What is the number of electrons that I need to add to that metal to get it back to its elemental form based on the reaction? So I convert moles of electrons to moles of metal, and then of course once I have moles of metal that I can easily get to mass of metal. So we can do this stoichiometry electrolysis. So I'm going to do a problem of this a little bit later on at the end, and come back and look at that. So the last little topic that I want to look at is what we call corrosion. So corrosion is essentially unwanted redox chemistry. So all the stuff we've been looking at is reactions that we're trying to get to happen. We're trying to get this voltaic cell to run. We're trying to get this electrolytic cell to run. Well, corrosion is undesirable, spontaneous redox chemistry. So by definition, we say it's the undesirable, spontaneous oxidation of a metal by oxidizing agents in the environment. So that's the definition of corrosion. More general terms, it's unwanted oxidation, right? Unwanted spontaneous oxidation. So the oxidizing agent here is typically oxygen, right? Can be other things, but oxygen is readily available in the air, right? So this is our most common oxidizing agent. And the metal ion so if we remember here, now these metals are often formed, right, by electrolysis, right? So if we think about it, a metal ion has to be reduced to form from its ore, right? So to get a metal from its ore, we're doing something like aluminum 3 plus 3 electrons goes to aluminum metal, right? So we're reducing that aluminum ion to get to its metal. So depending on how hard this is to do, right, it might be fairly easy to imagine this metal undergoing the reverse reaction spontaneously to produce the metal ions back. So it's not surprising based on what we've learned that metals like to be oxidized. And so the metals get oxidized back to what we might consider its more natural state, right? Most metals exist as their ions, right? This is sort of the stable state for most metals, not the actual metallic element. So we see that a lot of metals, right, will gradually over time oxidize back to the ion form. Now, the reduction here is typically, again, the reduction of oxygen gas. And so this is a fairly easy reduction, right? It has a positive 0.4 volts reduction potential, right? We see oxygen converts to hydroxide, or going from 0 to minus 2 in the presence of water, right? Now, if you make that acidic, right, so if you have acidic conditions, this is even an easier process because now, in the presence of hydrogen ions, we form this, we can take oxygen, reduce it all the way to water, right, to go from, 0 to -2 with a much higher voltage. Now, you say, oh, acidic conditions. Well, this is not hard to get to, right? Because most water that we deal with is already has hydrogen ion, has acidic ion in it because of the presence of dissolved CO2. Makes carbonic acid. And so having acidic conditions is pretty easy. And so what this is driving home is that it's pretty easy for oxygen to undergo reduction. We have a pretty high reduction potential here. And because the reduction of most metals is much harder than this, right, then the oxygen is going to undergo reduction, and the metal, the spontaneous version, is going to be the oxidation of the metal, right, with the reduction of the oxygen instead of the other way around. Now we're going to look at the most common form of corrosion, which is the rusting of iron. So just to kind of walk through the basic steps, at the anode here, initially, iron is oxidized to iron +2. The electrons produced in this process will travel through the metal, right? That's your conductive pathway, your wire, if you will, until they reach a place where they're exposed to oxygen, where the oxygen will be reduced in the reduction reaction that we just talked about. Now again, if we have acidic conditions, so if we have CO2 dissolved in moisture, right, in water drops, again, not that uncommon to have, small drops of water around, right? Then the iron can migrate, it's now aqueous, right, in the water, can migrate through this moisture to what we might call a cathodic region, where again it's exposed to more oxygen and is oxidized even further to iron +3, and this combines with oxygen and water to form what we commonly know as rust, or iron 3 oxide hydrate. Now, in order for this to occur, we need a few things to be true. So we have to have moisture, right? Water must be present. Water is a reactant in this process. So the rusting of something is going to be expedited in the presence of high moisture, high humidity environments, right? If you can keep a very low humidity, very dry, right, we can reduce the amount of rust that occurs, right? Now, in nature, this is not typically possible. Everything is moist. You need the water because you need ion flow between the cathodic and the anodic region. So ions will flow through the water, right, aqueous, and this is accomplished by tiny water droplets on the surface of whatever we're working with. If this is an electrolyte solution, again, very common because we have lots of ions dissolved in the water, right? This is going to give you better current flow. It's going to, again, expedite the rusting. So acidic conditions will make this faster. High salt content or high electrolyte will make this faster, right, and promote the rusting. Okay. So we already talked about the easier to reduce oxygen if we're in an acidic environment. So if we look at a basic picture here, if we take a real zoom in here, and if we have a water droplet present, so typically rusting will take hold where you have some sort of imperfection in the surface, and so we have exposed iron So even if we had some sort of surface protection here, like a paint, we have an exposed place in the iron, we can get the oxidation of the iron here. Now, once these iron plus 2 ions are formed, they're going to be solubilized, right? So they're going to be able to dissolve in this water. So they're going to be free flowing. And okay, so now we have dissolved iron. We have, as these electrons are being produced, right, the electrons are going to flow right here. And see, they're flowing through the metal. And once they reach sort of the edges of this drop, so they reach someplace where they're exposed to oxygen, then we get the reduction of oxygen. Again, produce the water here. So we have our initial redox chemistry, but now we have the iron dissolved in here. That iron will migrate to where it can see, again, the edges of these drops, where again it's exposed to both water here and oxygen. And those iron 2 ions can undergo further oxidation in the presence of oxygen and water to give you your actual rust, your iron 3 oxide. So for rusting to occur, you have to have access to both water and oxygen. So common ways that we try to prevent this, right, are preventing exposure to this, right? We'll cover the surface so that the iron is blocked, right? So it can't get contact with the water and the oxygen. Or if we don't do that, we'll store them in moisture-free environments like oil, right, if we're trying to prevent them, right? So we're going to do some sort of way to prevent exposure to water and or oxygen, which are both necessary for this rusting to occur. Now, if we want to prevent corrosion, there's many ways that we've done it. We're just going to briefly talk about a couple of ways. The most common way, again, is a surface protection. The most common type of surface protection is a simple paint, right? A simple coating, right? Where we spend all kinds of money keeping our iron surfaces covered, like painting our cars, painting anything that's made of iron, to block that exposure, to stop or slow down the rusting of our iron. Now, some metals naturally protect themselves. So things like aluminum and copper will undergo surface oxidation, but then unlike rust, right, one of the issues with rust is that it's very flaky. So even when it forms, it flakes off and exposes fresh iron. With the oxides of aluminum and copper that are formed, they're very sticky, right? They stick to the surface and they form their own surface protection. So for aluminum, it's kind of a hazy white color. This is, we say aluminum doesn't oxidize. Well, we make stuff out of aluminum to be outside. Well, the truth is it really oxidizes, but once it surface coats with the oxide, then it stops. The copper also forms a nice surface product of oxidation. We call this a patina, right? And it's that nice sort of blue-green coating that that forms on copper when it's exposed outside. But they attach to the surface and they prevent further corrosion. So these are simple surface protections. Now, another way that we can do it may also give us a surface protection, but also gives us an electrochemical protection. And this is called using a sacrificial electrode, or more specifically, a sacrificial anode. And what this basically entails is providing an easier to oxidize metal. So that may be providing a some sort of metal that is easier to oxidize, like, for example, galvanized nails, right? These have been coated with zinc. So we take a basic iron nail, we coat it with zinc. Zinc, if you look at your reduction potentials, right, is going to be more negative or easier to oxidize than iron. And so as long as that easier to oxidize metal is present, then that's the one that's going to be oxidized. So we talked about the opposite in electrolytic cells. If we had a mixture of metal ions, that the one that's easiest to reduce would be reduced, right? Same thing here. If we have two metals, the one that's easiest to oxidize will be oxidized as long as they're in physical contact with each other, or at least electrical contact. Now, we also do this in larger applications, say metal pipelines or ships or large steel towers. We will attach what we call a sacrificial electrode. Again, those are typically made of zinc or sometimes magnesium, and they'll be attached via some sort of metal cables, usually, or physically attached to the surface of the metal. And again, as long as that sacrificial metal is in electrical contact, we can prevent the metal that we want to keep from being protected. So again, this is often used in large steel structures, especially in remote areas, or pipelines that are buried or even above ground, right? Instead of a very expensive process of constantly maintaining and painting these large towers and pipelines, to prevent the iron from rusting, we simply attach at every so often these sacrificial metals, and those metals will then undergo the oxidation process, saving the iron. Okay? So, preventing corrosion. We have several ways to do it, but they all essentially involve either a coating to prevent exposure to water and oxygen, or an electrolytic protection in the form of a sacrificial anode, or again, electrically attaching or physically attaching, right, putting them in contact with an easier to oxidize, a sacrificial metal. Well, that wraps up our discussions in Chapter 20. I will be, again, doing a practice problem here to follow up, looking at the stoichiometry of electrolysis. With any questions, make sure to contact me for further explanation.